The universe's edge is a fascinating concept that challenges our understanding of space and time. You might wonder what is beyond the edge of the universe, or it's just infinite. Let's break this down in a simple way. We talk about the observable universe, which is the part we can see and measure. It's 93 billion light years across with a radius of 46 billion light years. This edge is actually the limit of what we can observe, not a physical boundary. Beyond this, there might be more universe that we can't see or interact with. General relativity suggests the universe is flat and could go on forever. However, measuring the universe's curvature precisely is incredibly challenging. The flatness doesn't mean a two-dimensional surface, but rather that the rules of geometry we understand, like parallel lines never meeting, apply on a cosmic scale. Some argue that since we can't interact with or observe what's beyond the observable universe, it's not a scientific question. However, science often explores the unknown, even if we can't directly measure it. The observable universe's edge is tied to the particle horizon, the furthest distance from which light has traveled to us since the universe began. This horizon defines the known universe's boundary. But reaching the particle horizon is not straightforward. The universe is expanding, meaning the further we try to go, the more space stretches. To visualize this, imagine traveling towards a distant point while the ground beneath you stretches out, making the journey increasingly longer. Even if you traveled at the speed of light, you'd never actually reach the particle horizon because space continues to expand. This expansion leads to the concept of an event horizon in the universe, similar to the event horizon of a black hole. Beyond this point, even light can't reach us because space is expanding too quickly. Thus, the universe's edge is not a solid boundary, but a limit of what we can either observe or interact with. In simpler terms, while we have a measurable edge to our observable universe, the true extent of the entire universe might be far beyond our current understanding or reach. The expansion of space means that parts of the universe are forever out of our grasp, creating an infinite journey towards an ever-receding horizon. This infinite nature makes the universe both an endless source of curiosity and a profound mystery. Just imagine the universe as a vast, ever-expanding bubble. Within this bubble, there's a boundary called the event horizon. Beyond this event horizon, nothing, not even light, can ever reach us. This is because the space beyond this point is expanding so rapidly that even light, the fastest thing in the universe, cannot bridge the gap to get to us. Currently, our best measurements suggest that the event horizon is about 16 billion light years away from us. This means there are galaxies we can see now, but they are so far away that any new signals they emit will never reach us. It's like watching the light from a distant ship that's already sailed beyond the horizon, where we'll never be able to contact it again. There's another boundary called the particle horizon, which is the edge of the observable universe. This is the farthest distance from which light has had time to reach us since the beginning of the universe. Interestingly, the particle horizon is farther away than the event horizon, so there are regions of the universe we can now see thanks to the light that left those places long ago, but can never actually reach or send signals to because those regions will move away faster than the speed of light due to the universe's expansion. As the universe continues to expand, more and more of it will cross the event horizon, moving out of our reach forever. This means that over time, we'll lose the ability to observe or interact with many parts of the universe we can see today. It's a bit melancholic, knowing that as time goes on, we'll be able to see less and less of the universe. But what if we could break this cosmic speed limit, like the theoretical Alcubierre drive, which bends space-time to allow faster-than-light travel? We could potentially reach beyond the event horizon. Let's imagine we have such a spaceship, and we use the energy of entire stars to power it, chasing after the particle horizon. What would we find? Even if we could instantly travel to the particle horizon, we would simply see more of the universe. This is because the particle horizon is not an absolute boundary, but rather the edge of what we can currently observe. If you move to the edge of the observable universe, your new vantage point would have its own observable universe around it. The Milky Way would appear as a small part of the cosmic microwave background, the leftover glow from the Big Bang, in this new observable bubble. You would see a similar distribution of galaxies and clusters all around you, just as you do now. So, even with a warp drive, you wouldn't find anything fundamentally different. The universe would still appear vast and filled with galaxies, just from a new perspective. It shows that no matter where we go, the universe remains a large, intricate expanse, always offering more to explore, but with the same similar patterns. Beyond the edge of the observable universe lies a realm that depends on the geometry of the entire universe. On a small scale, the universe appears bumpy because of stars and galaxies, but on a large scale, it's quite smooth, like gentle waves on an ocean. Observations of galaxies in the cosmic microwave background, CMB, indicate that space-time is very flat. If space-time is perfectly flat, applying Einstein's equations simply suggests that the universe is infinite. If the universe is infinite and we somehow cross the particle horizon, the universe would continue endlessly. This concept of infinity is fascinating and complex, with some types suggesting infinitely repeating versions of our own universe. However, it's uncertain if our universe is perfectly flat. Consider the Earth. It looks flat locally, but from space, its curvature is evident. The universe might also have curvature that's too subtle to detect with our current measurements. If this curvature exists and is positive, the universe might be like the surface of a hypersphere, the 3D surface of a 4D sphere. In this scenario, traveling in a straight line through the universe could eventually bring you back to your starting point. Recent estimates suggest that if the universe is curved, the minimum radius of this curvature would mean traveling at least 18 times the distance of the particle horizon to complete a loop, assuming the universe's expansion halted during the journey. However, this idea relies on straightforward applications of Einstein's equations. While general relativity is powerful, it's not the ultimate theory of everything. There are intriguing ideas about cosmic inflation, suggesting our universe could be a slowly expanding bubble in a vast, exponentially expanding multiverse. These bubble universes might be finite in size regardless of their internal geometry, possibly having a true edge. What lies beyond such an edge is unknown. The laws of physics or even the numbers of dimensions might differ. Addressing whether it's contradictory to use Einstein's theory to validate itself, testing a theory indeed involves using it. Yet, relying on a single prediction isn't enough. Multiple consistent predictions strengthen the theory's validity. For a scientific model to be accepted as a theory, it needs to make multiple accurate predictions. General relativity is one such theory with many successful predictions. For instance, GR can predict the orbits of planets around the Sun. By studying these orbits, we can calculate the Sun's mass. Then, using this mass, we can predict how much light will bend when it passes close to the Sun, a phenomenon known as gravitational lensing. The predictions made by GR match the observed deflection of light perfectly. This same principle applies to galaxy clusters. By observing the orbits of galaxies within a cluster, we can estimate the mass of the dark matter present in the cluster. The gravitational lensing caused by the cluster should match this mass, and indeed, it does. Someone asked why stars and planets aren't filled with dark matter. This is an interesting question. Dark matter is described as cold and clumpy, meaning it gathers to form galaxies. However, it doesn't interact with itself except through gravity. This lack of interaction means dark matter can only clump together to a certain extent. For dark matter to collapse into a star-sized object, it would need to lose a significant amount of energy. Losing this energy is difficult without electromagnetic interactions, which dark matter doesn't have. In contrast, the hydrogen gas that makes up much of our galaxy can clump together into large clouds. These clouds can radiate light, allowing them to cool further and collapse into stars. Dark matter cannot radiate light, so it remains more spread out or puffed up compared to regular matter. General relativity remains one of the most successful theories because it can make precise predictions about various phenomena, from the orbits of planets to the bending of light around massive objects. Dark matter, while still a mystery in many ways, follows different rules than regular matter, explaining why it doesn't form stars or planets. So, what do you think lies beyond the observable universe? Let us know in the comments below, and if you'd like to see more content like this, don't forget to like and subscribe. Plus, if you're interested in knowing more about what lies beyond our Earth, don't forget to watch our video on Fermi Paradox and Top 12 Most Terrifying Planets Ever Discovered.